Thank you. So, as Philip pointed out, I basically work on learning theory, and so this is basically a theory talk. I'm not going to show you the best numbers, and what I would be talking about is some things that we've been working on in my group over the last couple of years. So, if you open a machine learning textbook, so this is kind of the first thing that you see, right? So, this is the setup, the statistical learning framework, the so-called famous statistical learning framework. You have your training data, you use it to train a classifier, and then you test it on test data, right? And the training and test data are drawn IID, independently from the same distribution, right? And then what you care about is high test accuracy. So if you can get high accuracy on your test data, or if you can get high accuracy with, or ideally if you can get high accuracy with respect to this underlying data distribution, then that's the gold standard, right? You're very happy, it's all good, you're very happy, right? Reality, however, is a lot more complicated, right? And if you are actually trying to use machine learning in reality, there are many other issues that show up. So, and just a small example of this is robustness. Your classifiers might work just on the distribution, but if you move a little bit from it, things may not work. Then there are things like sample selection bias. So the data that you got for training and the data that you get from testing, they might be drawn from slightly different distributions, and you may have to do something to correct for that. Then there are various other issues like privacy, some fairness, and things like that, right? And what we have been working on in my group is basically foundation. So this is what I call reliable learning in some sense. Broadly not accuracy, right? Broadly going beyond accuracy, and this is the kind of things that we've been looking at in my group for the last several years. And today what I will do is I will talk about two aspects, two challenges, and what we've been doing in addressing some of some work in each of these two challenges. And again, this is going to be a theory talk, so it's it's about the foundation, it's about understanding what's going on. It's about it's a theory, it's essentially a theory talk. Okay, so what is sample selection bias? Let's say you get a whole bunch of observation, training data, which is, I'm just calling it observational data, which is collected conditioned on some collection policy, right? So an example of this could be, let's say you have a bunch of data on treatments we're giving to patients, and you have some properties of the patients, and you have a bunch of data on whether the treatment was effective, right? And what you want to know is you want a classifier that will predict when the treatment works or not. If you think about it, your data is actually not drawn from the entire population on which you want the classifier to work, because what might have happened is that maybe the treatment was not always given, right? Maybe the treatment was given to patients with a certain kind of characteristic, maybe the treatment was not given to minors, things like that, right? So and if you don't take this kind of thing into account, what could end up happening is you can end up getting a biased classifier. Okay. And another example of such a thing would be predict if an ad will be clicked on based on logs, right? And this is it's very common. A lot of the companies which display ads, they have a whole bunch of logs where they have data on which ads were shown to users and whether the user clicked on it or not. But then these ads are shown based on some policy, right? There's some policy which determines which ad is being shown to which user, and if a different policy had been followed, I mean, we don't really know what the outcome would have been, right? And so if you want to build a classifier that predicts if the ad would be clicked on or not, you need to do something, right? It's not just enough to look at this data, okay? And so what could go wrong? And here's kind of a toy example. For example, if you're in your observational data, if you miss out those points which are white, what could happen is you could come up with the blue classifier, which is suboptimal on the entire population, right? So that would be an example, kind of a toy, concrete example of the kind of things that could go wrong. So what can you do? So one plausible solution is, you have your observational data, you fit your classifier. But the problem with that is you will end up with solutions like this. So these are high bias solutions. It works well when you're conditioning on the policy. It doesn't work well on the entire population. It's a local optimum. Okay. The second one is, this is one of the things that people do. You look at an importance weighted loss. So what you could do is, if let's say you know the policy, and sometimes you do know the policy. In the ad delivery case, you do know the policy that you use to choose the ads. Sometimes you can estimate it. Let's not go there, but let's say you know the policy. It's hard enough when you know the policies, trust me. So if you know the policy, then what you could do is you could reweight things, right? So you could give higher weight to things that would not be, that are chosen less frequently by the policy. And this is called the importance weighted loss, and you could minimize that. And that would give you a solution which is unbiased, but what would happen is you would end up with high variance, right? And that's kind of one of the standard approaches, okay? And what we would be doing over here is our solution is active learning. It's based on active learning. So we build a classifier based on the observational data. Then we assume that we can choose, imagine if you have a bunch of observation data, then let's say you can decide to give the treatment to a few people and see whether they respond to the treatment or not. And you can do that actively. And by using the observational data, you can get away with a few label queries, right? With a small number of label queries. So there's a couple of baselines here. So one is only using the observational data. By doing some extra active learning, we hope to do better than that. And then the second baseline is doing active learning from scratch. Using the observational data, we hope to do better than that. And the challenge here is just sort of algorithmically, information theoretically, the information is all there, but as we will see, it's not that easy to algorithmically combine these two and put together something which takes the observation data into account and also does active learning properly. Okay. So that's what I will be talking about. Okay, so let me start with a little bit of background on what is active learning, and then I will talk about how to use it with observational data. Okay, so what is active learning? And this is kind of a basic problem in machine learning that a lot of people have been working on. Remember, in standard machine learning, you have xi's, yi's, right? Xi, yi pairs, and you want to find a prediction rule that predicts y's from the x's. Okay. In active learning, you have a whole bunch of xi's, but instead of having all the yi's all together, you can make interactive label queries, right? So for example, and this is motivated by the fact that very often it's very expensive to produce annotation, right? You can download a lot of images from the web, but labeling them, somebody has to sit down and label it, and it takes time, effort, so on and so forth, right? So, so you can get to make interactive label queries, and the hope is that by using interaction, you don't need as many label queries, right? So if you do things interactively, you want to find a prediction label rule that will predict the y's from the x's using just a few label queries. You don't have to label the entire data set, hopefully, because of interaction. Okay, so why does this help? Let me again, try to convince you that it helps by showing a very toy example. So let's say you have, these are all your unlabeled data points. You have this red point, and now maybe you label this one, you get a black. You pick that one, you get a red. You ask the label for this one, you get a red. And now the only thing, if you are looking for a linear classifier, the thing that fits is this linear classifier, right? And what this tells you is that what you see from here is that you didn't really need to find all the labels of those white points in between. You just got away without labeling this entire data, right? So this is kind of a toy caricature example of why this helps. And you can also find, you can show more complicated other examples. Yes.
You can pick these xi's the way you want, and you guarantee to get the label.
Yes. Yes. Okay, so here what you are assuming is that the xi's, a set of xi's is given to you. So you can't synthesize random things. You are given a set of images, you can ask for their labels of any subset. Yep. Okay. But the challenge in active learning, and this is what makes it really hard, is the so-called incorrect responses, right? So what do I mean by this? So remember, this was what I got over there. And if my data really looked like that, right? So there, if you look carefully, then this dashed line is what corresponds to the best classifier, right? But the best classifier is not a perfect classifier, right? The best classifier, makes some mistakes. And because we had chosen our initial queries not very aptly, we ended up zooming on to this classifier on, the solid classifier, and that is a suboptimal classifier. And more active learning would not have helped you there, because if you did more active learning, if you looked at this kind of strategies, what you would do is you would keep querying for labels around that black classifier, right? Just because you started in that particular way, you got diverted to this path, you decided to ignore this entire region of space, and you got stuck in this local minimum, right? And if you don't do active learning carefully, if your data was perfectly consistent with a line, then you would be okay. But if that was not the case, then you could get into these kinds of situations, right? And this is the thing that you have to be very careful about in active learning. And, not just active learning, any kind of interactive learning process. Yes, question?
Can we think about misspecification in exactly the same way?
Misspecification.
Your model more linear?
Yes.
Is there some equivalence between these two?
That is an excellent question. Yes. So when you have model misspecification, you can show these kinds of examples. Exactly. Yes. If you don't have model specification, if you have either perfect separation, or if you have benign noise, then active learning works reasonably. The kind of things that you would think of would work, they work reasonably well. If you have misspecification, these kinds of things happen. Yes.
Maybe this was the same question, but so this counterexample is in the unrealizable setting.
Absolutely. Yes.
In the realizable setting, you're saying things would work.
Yes. In the realizable setting, active learning works very well. Yes. That's absolutely right. Absolutely right.
What
Yes.
do you mean by benign noise then?
Benign noise, I mean things like, random classification noise or noise close to the boundary, things like that. Then, even then things just sort of work. You have to be a little bit careful in how you cancel things out.
Oh, so those two red points up there are not
Yeah.
right?
Yeah. There's a bias, yeah.
Okay.
Yes, thank you. Yes. Okay, so you have to be very careful when you design your active learning algorithms, because that's kind of a pitfall. And any kind of interactive thing, you have to be careful with these sort of effects. Okay. So what are we going to do? So there are a class of algorithms that they're called agnostic active learning algorithms, which do work in this situation. And what we will be building on is something called disagreement-based active learning, which a lot of people have worked on. So, this the first algorithm was introduced by Cohn, Atlas, and Ladner, way back in '94, and then Balkan et al. Have, I think Balkan, Begenzheimer, and Langford, kind of brought it back in 2006, and since then, a lot of people have looked at this line. And there are actually pretty practical algorithms and, implementations out there. So it's not just something in theory, it actually also works in practice. And here is kind of the overall idea for this. You maintain a candidate set of classifiers, V, that will contain, let's say, high probability contains the best classifier in your class, okay? Then you have a bunch of unlabeled data points. For each unlabeled data point, you check if there are two classifiers in your set V, whose labels, such as C1 and C2, which give it different labels, right? Which disagree. Then your X is in the disagreement region of this set of classifiers. You query the label of X, and then you update your set of classifiers, and you keep going, right? And update, and then you can keep doing this, running this process, okay? So how do you pick this candidate set, right? So remember I told you about how we are maintaining this candidate set of classifiers. Well, the candidate set is a 1 minus delta confidence set for the best classifier in your concept class. So what do I mean by confidence set? So I won't go. So I'll draw an analogy here. We have all done basic statistics. So think about it as an analog of confidence intervals, right? So if you have, let's say, you see you have a bunch of bits, 0, 1, IID. You see n bits. You can what is the probability of seeing a head? You can draw a confidence interval, right? You can say bit probability 95%, it lies in this interval, right? And similarly, you can think of confidence sets as well, right? So instead of thinking about this as intervals, you can think of a set of classifiers such that the best classifier with probability 1 minus delta is going to lie in this, right? So I'll just draw this analogy. And how do you pick the confidence set? Well, remember what we are looking at is confidence set for the C star, right? And what is the C star? C star is this thing that minimizes that particular sum. So that sum is, 1 over n, sum over all your training points, C of xi not equal to yi. So this is kind of, in some sense, this is the empirical error, right? The training error. Okay, and now what you could do is, there are many people who have worked on generalization bounds, which are of the following form. I mean, I'm using something very loose over here. I think Philip can tell you that there are tighter ones, but and he's worked on some of them. And basically, what you can say is something like with probability 1 minus delta, error of C for all C altogether in your concept class, error of C minus error hat is at most something like this, right? Square root of the VC dimension of the concept class times log of n over delta divided by n, right? So square root is something like this. So you can get this. There are these generalization bounds that a lot of learning theorists have worked on. And so you can use this and say that I will pick all concepts whose empirical error is at most the minimum empirical, minimum training error plus this particular term, right? So let's say, I could do that, okay? And that is going to be my confidence set. Okay, so let me mention one thing in which I won't go into. So when I talk about maintaining this confidence set, we are actually not going to maintain it explicitly because maintaining it explicitly is computationally hard. But what we are going to be, so a long line of work on disagreement-based active learning has shown how you can maintain this implicitly, this set implicitly, and you can test whether something is in the disagreement region of that set, right? So that testing you can do implicitly by doing two ERMs, basically by solving two risk minimization problems. So I won't go into that, but just suffices to say that this can be done with relative efficiency. But for the purpose of this talk, I'll just ignore it for the moment. Okay, so this is how we are going to maintain, let's just say, our confidence sets, okay? So there's two things to point out over here, right? One is that notice that, we were talking about this error hat C, right? And that is something that's going to be important when we talk about combining observational data. And so one thing is that there is an unbiasedness over here. So C star is the minimizer of error hat C. C star is the best according to the population on expectation and so on. And actually, sorry, it should be the expectation of error hat C, and that minimizer of expectation of error hat C, and that will give us statistical consistency, right? So if we have like a biased thing whose expected minimizer is not the best classifier on the population, then we might lose statistical consistency, and we have to be careful. Okay. The second point is that the fact that error hat C has low variance, right, that is actually a good thing. We want that sort of objective function to have low variance. Why? Because if it has low variance, that means our confidence set is tighter. And what does a tighter confidence set mean? Well, what that means is if it's a tighter confidence set, its disagreement region is smaller, and so we are asking for less labels. Because remember, we only ask for labels in the disagreement region of the confidence set, right? So tighter confidence sets is a good thing. That's what we want, okay? And we'll come back to this in a little bit, okay? Okay, good. So now I told you about active learning. How do we use this with observational data? Yes? Yes, yes. So that will come. So right now we are talking about the algorithm, but that will determine your label complexity, how many labels you need. Absolutely. Yes, that will come to that. Okay. Okay. So remember, this was active learning. We were using interactive. You have a question? Or?
Yeah, I think I missed a component. Are you going to tell us how to? So when you estimate your empirical error, you want your empirical error on the original distribution, but you don't have the labels from a small number of points that are not chosen at the same distribution.
Yes, so we'll talk about how to do that in a little bit.
That's not standard.
That's not standard, no. Okay. Yeah. So, okay, so we do this using a few label queries, and now we are going to do active learning with observational data where we have some sort of pre-collected observational data set S0. Let's just say it was collected by some known policy Q0, and now we have, let's say we have some observation data, we can ask for a few more labels. We have now some unlabeled data with respect to the population, we can ask for a few more labels, and now what we want to do is, get some prediction rule for the entire population using just a few label queries, right? And the challenge is again how to combine both, right? I mean, you could throw away the observational data, but we don't want to do that. You could use only the observation data. Also, we don't want to do that. We want to be able to algorithmically combine the two. Okay. Okay. So how do we use? Yes.
So the policy means that you come up with a sample xi, yi. You apply some sort of a predicate or
exactly. Exactly.
No, you say throw it away.
Yes, or it could be like a probabilistic thing also, right? It could be that with, yeah. So think about Q0 as a probability.
But still, it's a product measure.
That
can be xi's one at a time. Like it can be a bandit procedure, for example.
it could be. You really have no control over it. So long as you know it, we are happy. If it goes to 0, then things might blow up. But yeah. Okay. So how do we use observational data? So the first idea is, and it's kind of the most obvious idea is, we use it to do a warm start, right? You start out, remember you had to have your confidence set. You initialize your confidence set with the observational data, and, definitely that's something we must do. And how do we do that? Well, recall your V was your confidence set for this particular objective, which is basically the sum of the empirical errors. You could use observation data in the sum, but this will lead to a bias loss estimator, and so it won't be the right thing. So the solution is, it's kind of the first thing you would think about doing. The solution is importance weighting, right? So what you would do is, instead of using just the simple over the observational data, you use the importance weight, so 1 over Q0. So think about, Q0 xi is, roughly think about it as the probability of picking xi according to the policy, and this will give you an unbiased loss estimator, and which is a good thing, right? Which will eventually lead to statistical consistency, right? So this is how you start. Okay, so this is our first idea. Now, how do we combine this while doing active learning? So this is how we start. Now we are doing active learning. How do you maintain V? Okay, so one possible thing you could do is you have your objective that you got from the first part, right? It was an importance weighted objective, and then then the new samples that comes along, you do 1 over Q1 xi, where Q1 is the probability that your active learner is going to get is going to ask for the label of xi or picking of xi by the active learner times the whether you made a mistake on it or not, right? But the problem with this would be that the variance of this particular objective would be very high, right? And remember, variance high is a bad thing because that means lose confidence sets and things can go out of control, right? So what do we do? Well, and this is especially the case because really there's nothing you can control about Q0, okay? And the solution to that again is we use something called multiple importance sampling, which has been known in the kind of the MCMC literature for a while. Instead of using that objective, we use the objective below, where we are summing over S0 union S1, and then we are normalizing with N is the size of the observational data, and M is the size of the actively sample data, and we do this in batches, and so this is the objective that we use, and we can show that this objective has better variance, okay? And this leads to lower variance, which leads to better active learning. Okay, so now we know how to do some warm start. We know how to do the how to combine it. How do we query for labels? So the naive thing would be, if we were doing standard active learning, again, by solving this, by using the observational data, we already get a somewhat different candidate set V. Standard active learning would just query for labels in this disagreement region. But what we can do is we can do something a little bit better. We can query for labels in the disagreement region of V only if Q0 of x, so Q0 of x measures how well represented x is in your observational data, lies below a certain threshold, right? And if you can do this thresholding properly, then then you get the right kind of bounds, and that leads to lower label queries. So we can show that that leads to lower label queries. Okay. So these are basically the three ideas. Warm start. Then you combine properly the two objectives using multiple importance sampling, and then you undersample labels in the regions that are well represented in the observational data. So these are kind of the three algorithmic ideas that we use. Okay. So how does this work? So since this is a theory talk, I will give you the theory answer. So how do we measure how active learning works, right? And this is again comes back to Philippe's question. What we do is the following. So I will give you kind of the intuition. So what happens is, as you keep doing active learning, you have your the C star, right? The best concept that you're trying to reach. As you keep doing active learning, you have there are concepts around C star, and your candidate set is going to shrink around it, right? The radius is going to shrink, the candidate set is going to shrink around it, right? The label complexity, and so as the candidate set shrinks around it, its disagreement region is also going to shrink. There are some cases where it won't, and those are somewhat pathological cases where active learning doesn't help, and there's some cute examples where it doesn't. But mostly, as this candidate set shrinks, its disagreement region is also going to shrink, right? And basically, the label complexity of active learning is measured by something called a disagreement coefficient, which has kind of a complicated thing. But really what it is the rate at which the disagreement region shrinks, right? So as you shrink R, what is the rate at which the disagreement region of this ball of radius R around C star shrinks? That's the disagreement coefficient, and that's really what measures how well active learning works, right? This kind of disagreement-based active learning works. And so anyway, right? And there are also other names for this. I think Alexander's capacity and things like that. There's other names for this particular thing, but that's essentially what it is. And what happens is when you change the active learning model, as we are doing right now, if you have active learning with, for example, different kind of queries, or if you have, like weak and strong labelers, what happens is the nature of the disagreement region changes, right? So then, then you are sampling from some subset of the disagreement region. And in these cases, what happens is what you get is, instead of the disagreement coefficient, you get a modified disagreement coefficient, right, which measures how the sampling region changes as the ball of radius, as you get closer and closer to the closer to C star. Okay. And again, so these things typically in the worst case, they are the same as the disagreement coefficient. So which means that in the worst case, active learning, there's always some worst cases when things don't work as well. Sometimes, in the optimistic case, it works well. And, in active learning, it's always like that. In the worst case, active learning never works better than passive. Okay. So let's look at how we do. So if you did passive learning with importance sampling, this is the kind of thing you would get. So ignore the log H over delta that comes from some standard generalization bounds. But if you want to, if your nu is your error of C star and you want to get to nu plus epsilon, what you would get is something like 1 over Q0, where Q0 is the minimum importance weight, times nu plus epsilon over epsilon squared. Okay. Active learning, you have an extra nu times theta, and this is at most 1, and because of the way things are defined, this is at most 1, and this is actually quite common, right? When you go from passive to disagreement-based active, this is the factor you would get. Okay. Now notice that if you use multiple importance sampling, then you lose the 1 over Q0, which could be quite good. And finally, when you get to our algorithm, you get from theta to theta tilde, right? And, in the worst case, theta tilde could be the same as theta, but in the optimistic case, it's better because hopefully your observational data does help you learn. If it doesn't, then, there's nothing you can do. Okay? Okay, so in conclusion, so we have a new algorithm that, we use active learning to address sample selection bias, and then we can show statistical consistency, plus you need less labels than passive and standard active learning. We also have a more recent follow-up which is coming up in NeurIPS, where we can use, so instead of this kind of estimators, we use, so Thorsten, Joachim, and various other people have been looking at these variance regularized and importance weight clipped estimators, and we get them to work with active learning, and as you can imagine, it also requires a lot of engineering. So especially improving the statistical consistency, things like that. So we get them to work with active learning. So that's what's coming up in NeurIPS. Okay. Okay. Yes. Question.
You show a relation between theta tilde and theta as a function of something to do with the policy, right? So if the policy always says yes, then of course
Yes.
great.
Right.
But somehow, perhaps the probability that it's not yes and no, I understand, but
Yeah.
perhaps average value of the policy or something of that form.
We haven't looked into it, yeah. So what we have found is if you have like reasonable policies, so we also have experiments in our paper, which I'm not showing due to lack of time. But what we have found is that if we have, like it works when you expect it to work, right? Like if the policy does not exclude all examples in the decision boundary, close to the decision boundary, then it works better because you get something from the policy. Essentially. Okay, so I mentioned two practical issues. So we talked about sample selection bias. The next, what we will do is we will, take, change things a little bit around and talk about robustness. And, if I understand correctly, many of you actually work on this, right? So, adversarial examples, many of you seen this before, many of you already work on this. Basically, so this is kind of the canonical demo that is shown, right? So you have a neural network who's like, which is super confident and that this is a panda. You add 0.007 times that, and it's super confident that it's a given. Right? So, this is what we are using for our image detectors, right? So, there you go. So, that's your adversarial examples. And they're everywhere. And in fact, a lot of, so what people have seen over the last few years, and actually, people knew about them, not for neural networks, but people actually had come up with the notion of adversarial examples. In fact, in the mid-2000s, so there was this paper by Chris Meek and Daniel Loud. And also there were a paper by a group in Italy where, they had come up with these things. But, recently it has seen a resurgence because in neural networks, the examples are just so blatant, right, that you can't ignore them. So they have seen this resurgence. And the idea here is that you have a slight strategic modification of a test input, and that leads to a misclassification. That gives you a misclassification, okay? And in fact, many classifiers are vulnerable to adversarial examples, okay? So in this talk, we won't really look at the best kind of attacks or defenses for adversarial examples. So since I'm a learning theorist, and where I kind of come into the picture is I would personally like to understand why we have adversarial examples, right? Like what is going on under the hood? Why are they even there? I would like to, I like to do theory, right? So I'd like to understand why they're there, okay? So why would we even have adversarial examples? So let's look at what could be the plausible reasons, right? But what could be happening over here? Well, one possibility is that your data distribution, maybe the pluses and minuses are close together, right? And so if you change the pluses a bit, the data distribution is such that you would venture into the minuses, right? And there's not much you can do over there. So that would be, distributional, that would be characterized by something called distributional robustness, okay? The other possibility is that, maybe the distributions are not like that. Maybe your pluses and minuses are separated, but, you see too few samples and you can't really tell what's going on. And, you draw your decision boundaries. Maybe the black one would have been very robust, but instead of the black one, you drew the blue one because you didn't see enough samples, you didn't know what to do, so on, right? And then, of course, the other possibility is that we are really just using the wrong algorithm all along, right? Because we are just, we have our blinders on. We are so focused on accuracy that we are just using the wrong algorithm to, because we never even think about robustness. So we've been just using the wrong algorithms to find our classifiers, okay? And
so there's a fourth possibility, right? I mean, that there is no efficient algorithm.
That's also, yes, that's yes. There's also some, yeah. In some cases, yes, that could be definitely, yes. And the first one is, I mean, in statistical learning theory, the first one is just kind of analogous to what is called bias, and the second possibility is analogous to what is called variance, okay? And I will, kind of give you a high-level picture of the answer. So we have looked at it in the context of non-parametric methods, where the efficiency as such is not so much of a concern. So in some cases that is also definitely the case. Anyway, so and the answer is really a combination of 2 and 3. So there is some, too few samples and bad algorithms. So it's yeah, it's a combination of 2 and 3. Really, that's the answer. Okay. Okay. So before we get into kind of the theory, let me start out with the kind of framework that we are looking at. So we are looking at, the standard statistical learning framework. Let me start out by defining it. You have some sort of a metric space. X is, a space of instances, and then D is a distance function, right? It's a distance metric. It could be, L to L, infinity, anything. And you have some underlying measure mu on this instance space, okay? And the label of your, of each example is a coin. So there's an underlying measure. The label of an example X is a coin flip with bias probability y equal to 1 given X. Okay, and remember in this case the accuracy of a classifier, which is what people have been focusing on for so long, is it can be defined as, if you are given a classifier f, its accuracy is that probability of fx is equal to y, and the Bayes optimal classifier is kind of the, in this setting, it's the gold standard. It's the most perfect classifier, right? If you knew your mu, and actually all you need to know is that this py equal to 1 given X, then your Bayes optimal classifier is the one that will maximize accuracy. Okay? Okay, so now let's look at some definitions related to robustness. Okay? The robustness radius of a classifier f at a point x is the distance to the closest z such that fx is not equal to f of z. So basically, distance to the closest point where the label gets changed, right? And we are just going to kind of denote it by rho of f and x. And if you have a classifier that has a high robustness radius, that's a good thing, right? It means your classifier is robust at x. But notice this is a point-wise thing, right? A high robustness radius at a particular point, okay? And yes? So here, I'm leaving the distance somewhat unspecified by design, but yeah, but you can define it with respect to any distance you like at this point. So we'll come to that in a bit. Okay.
Is that the ground truth or the
Our classifier. So we are talking about the robustness of a specific classifier, not necessarily the ground truth at this point. Okay. Okay, so now, remember we were talking about accuracy, right? So, and in machine learning, so far we have been, we have been focused on accuracy. What is the analog for robustness, right? That combines accuracy and robustness. Well, we came up with this name astuteness because, the classifier is very sharp and astute. And so the astuteness of a classifier at a robustness radius R is basically the set of points where the classifier, with respect to the data distribution, where the classifier is correct and it takes the same value, right? It is robust with radius R, right? So not only is it correct at that point, but it gives you the same prediction in a ball of radius R around that point, right? And there may be some points where it's correct, but in a ball of radius R it does different things. We are just not going to count those, right? That's your astuteness, okay? And then the goal of robust learning is essentially to maximize this astuteness, okay? So this is the kind of thing that that we are looking to do, okay? And so that's kind of our goal, okay? Okay, so prior work, people have, so here we are going to talk about, non-parametric methods, and, the paper I'll be talking about is, work done in 2018. So prior work has looked at parametric methods, and I think some of you have also worked on this before. Schmidt et al. Looked at linear classifiers and gave an example with a mixture of two Gaussians where adversarial robustness would require more data than accurate classification. In fact, Bubek et al. And I think there's been more work in this area where it has been shown that achieving robustness may be more computationally challenging. I don't know if you have a paper on that, but you do. Okay, excellent. So Vinod also has a paper on this, but there's been a line of work, started by Bubek et al. There are many more works on this, including some of Vinod's. There's been some other work which has looked at, there's a group from TTI Chicago, Montesser et al., and then also there's a group at UC Berkeley who have looked at bounds on adversarial generalization. So Rademacher complexity, when you apply it to adversarial generalization, what does it look like, right? So that's there's a group which has been looking at that. Okay, so this is kind of prior work. In this work, we are just going to look at something a little bit different. And mostly, so this was in 2018, and mostly because it's just easy to analyze, right? So it's easy to analyze, it's easy to understand what's happening. What we look at is when is nearest neighbors robust to adversarial examples, okay? So, everybody knows what's nearest neighbors. So basically, if you don't, it's basically you look at, for every point X, you look at the K points closest to it and look at its average label, right? That's your, look at the majority label, and that's your prediction. Okay, so here is the first thing we can show. If you are looking at one nearest neighbor, then if your data distribution is, then your mu, the distribution on the axis is continuous, and if in a neighborhood of x, your py equal to 1 given x is not 0 or 1, right? It lies strictly between 0 and 1, then your robustness radius will go to 0 as n goes to infinity, right? So things like one nearest neighbor is not at all robust. And this is not super duper surprising or not at all accurate, right? So in this case, so one interesting thing is that the accuracy in this case could be quite high. So if your, py equal to 1 given x was 0.999, your accuracy could be quite high, but your astuteness would be just 0. Right? And it's not super surprising because as you, in this case, what would happen is there will be some point that's arbitrarily close to you which has a different label, and that's your adversarial example. So it's not surprising, but the interesting thing is that, in this case, even though your accuracy is high, your astuteness could be quite low, and you could have arbitrarily close adversarial examples, essentially. And then, the other thing that we can show, again, not super surprising, is that this can hold for constant k. Okay, so even if your k was constant for k nearest neighbors, you can, this will also be true. Okay, so constant k, we have resolved the situation, it's not robust. What about larger k? Let's remind ourselves what happens with accuracy for larger k, okay? So for larger k, so here is something that we can show. This is like standard non-parametric theory, statistical learning theory. People have been able to show this a long time ago. Basically, if your k grows with n, such that as n goes to infinity, k also goes to infinity, and k over n goes to 0, then the accuracy of k nearest neighbor converges to the accuracy of the base optimal. And kind of the intuition, the proof is a little bit more complicated, you have to do things properly, but the intuition here is as, n goes to infinity, you are getting more and more local, right? You're getting more and more local around a point. And also, you're getting more and more accurate because you're averaging over more and more points, right? Your kn goes to infinity means you average over the labels of more and more points. So your estimate gets more accurate, you get more and more local. N goes to infinity, you're doing the right thing, right? That's kind of the intuition. And you have to work things out and so on. Okay, so that's the idea, okay? Okay, now let's look at robustness. What about robustness? Well, yeah. Yes. Kn has to be little o of n, because otherwise you can't be, you can't be local, right? Okay, good. So for robustness, what can we expect? Well, you know, the best we can expect, so nearest neighbor n goes to infinity, you are getting to the base optimal, right? The best you can expect is you are robust where the base optimal is robust, right? I mean, there's no magic. There's nothing's better than that is going to happen, right? And in fact, we can show such a thing, but what we need is what we need more than what we need for accuracy. And what we can show is, we can show that the robustness regions of k nearest neighbors would converge to the robustness regions of the base optimal if your n goes to infinity. You know, of course, kn over n has to go to 0, the locality you have to have. But if kn grows at least at the rate of square root dn log n, right? And, you know, I mean, for the theorists in the audience, this comes from something called uniform convergence, I think, in balls round. But essentially, so, you know, if you didn't understand that, ignore it. But essentially, we don't have a lower bound, but essentially our upper bound, to show our upper bound, we need a much higher k than what we would need for accuracy, okay? So, so this also translates to more data, and I will tell you why. The reason is, if you want to be at a certain level of locality, and if your k is higher, that means your n also has to be higher, right? So so for example, if you want to be, let's say, within 3 inches of this particular point, and you need there to be 20 points, then, you know, your n needs to be higher than if you needed there to be just 5 points, right? So you need to be more dense, right? So in that sense, this translates to an upper bound that requires more data, right? So, you know, if you remember, we talked about, you know, why do we not have robustness? We talked about, you know, maybe we don't have enough samples. So this is connecting to that. Okay, yes, question?
Oh yeah, I just wanted to ask, if you wanted like a non-asymptotic guarantee, is there like an obvious choice for like what value of kn you should pick? Like say to balance off like accuracy and...
That's an excellent question. I don't know. There are many open questions. Yeah, yeah. Like
what I actually wanted to understand was like, oh yeah, imagine there's a good value in the case where you just want accuracy and not robustness, and I wanted to know if that's bigger or smaller than the root d and log n.
Oh yeah. That could be much smaller. Yeah, okay. That would be much smaller. Right. Yes. So it just kn has to. Yeah. Yeah. For rates, you can give precise rates. Yeah. Yes. Excellent question. Okay, so root d, where does d come from? D is, so this holds when your metric for nearest neighbor matches the metric for the adversarial robustness, and this d is actually the VC dimension of balls in that metric. So this is, you're right, this is for, you know, so this is for L2, but if you have, so basically this is a VC dimension of, you know, so you can do other metrics, the same proof technique would apply, but instead of D, what you would have is VC dimension of balls in that metric.
So for N infinity would be just D?
Yeah, I guess O of D maybe, yeah, essentially, yeah. But then it has to be L infinity nearest neighbors too. So that has to match the metric, yes, that's the condition, yes. Okay. So now the question is, you know, we talked about robustness for, you know, k nearest neighbors, for, you know, k being very large. Now the question is, can we get robustness for 1 nearest neighbors? And now we will come back to this other aspect that, you know, maybe we are using the wrong algorithm. And the answer is yes, but we need to change our algorithm. Okay. So, so we can show a modified algorithm. So to motivate the algorithm, let's start by thinking about when is nearest neighbors robust, right? And, you know, when is it robust? Well, it's going to be robust when points with different labels are well separated, right? And it's going to be robust at x, and its x is close to a point which has the same, you know, which has the right label, and then different labels are well separated, so its nearest neighbor is not going to be a point from a different label, okay? So, so then, you know, what can you do? Well, you know, this already suggests some sort of an algorithm. You have your training data, you remove some part of the training data so that the differently labeled points are far apart, and then you do nearest neighbors on the rest, okay? And which points do you remove? Well, so something that you could do is, if you have some points where you are very confident about the labels, then you keep those around, and then you keep a maximal subset of the rest, right? The points where you're confident about the labels, you just kind of have to keep them, and then, you know, out of the rest, you could keep, might as well keep the maximum subset, because that will give you a high accuracy. Okay? Yeah, sorry.
How do you measure your confidence in the label?
Yes, so we're coming to that in just a little bit. Okay. Okay, so so how do you do? So I'll you know, give you one more definition. So we say that you have a set of label points. They are separated when points with different labels are at least 2 arc distance apart. Okay. And here is Philippe's answer. I planted him in the audience. So here is the answer to your question. So you, how do you get confident labels? You look at points, you have your input, you know, it's an X. You have a training data of size N. You have parameters, you have, these are basically parameters in your Chernoff bound. And you look at, you select Kn, and it's, kind of selected nicely to make Chernoff bounds work out. You look at the average of Kn labels, of Kn points around you. And then if the average is within half minus delta and half plus delta, then you return don't know. Otherwise, you just round it up and you return the rounded value. Okay, and that is your confident label. So your confident label could be either don't know, if a bunch of points around you give you, their averages are just sort of uncertain, or it could be plus or minus 1. Okay. And here is your full algorithm. You look at the confident label of all your data points. You start out with an empty set, right? And for all your data points, if your confident label is the right label, and also if the confident label of all other points in a ball of radius r around you are the same, then you just add it to the confident label set, right? So these are the points that you must keep. And then you just return the largest R separated subset of the training set that contains these confident points. Okay, and I won't go into too much detail of how this can be done, but this can be done through kind of a maximum matching thing. Especially for 2 labels, you can reduce it to a slightly modified maximum matching problem. For more than 2 labels, it's a vertex cover problem. You can do a greedy algorithm. It's not exact, but greedy algorithm is reasonably good. Okay, so this is how it can be done. And
for all xj, you don't do for all xj, but rather you subsample or something.
Yeah, so for all xj, yes, in your training set. Yeah,
Oh, I see.
in your training set, yes. Yes, yes, that's right. So when is this algorithm robust? Well, I won't go into the exact mathematical details of exactly the exact mathematical expressions, but basically what you can show is that the robustness region of this algorithm converges to dense subsets of the robustness region of the Bayes optimal classifier. Right? And what do I mean by dense subsets? Basically, you need over a threshold number of samples from the region. If you have too few samples from that region, you would probably rule those out. But if you have enough samples from the region so that you have those Kn points and you can do that thing, then you will keep those things around, and then things will work out. Right? So it's dense enough subsets of the Bayes optimal classifier. Okay? And experimentally, what we can show is that it works well with reasonable n. So I have a couple of small experiments. I won't go into too much detail, but essentially, we look at standard nearest neighbor, our method, and adversarially trained one nearest neighbor with a couple of different kinds of attacks. Basically, what we can show is something like this. On the x-axis, you have the norm of the perturbation, and in the y-axis, you have the accuracy. And what you can see is the orange line is our method. Overall, the orange line goes down more slowly than the others, right? So the red lines are, I guess the blue is standard, red red and green are different kinds of adversarially trained, and the orange line goes down more slowly. And the other thing is that adversarial training doesn't work too well, and this has been noted for non-parametric methods. The fact that this happens has been noted before, right? For neural networks, adversarial training works very well, but the fact that it doesn't do so well for non-parametric methods has been noted before. We are not the first people to find this. The attack was, so one was a direct attack, so this was a published attack on nearest neighbors. The second was, and which was the best at the time. Second was I think we took a kernel substitute, so a kernel classifier, and then we used the gradient-based attack. So these two were the best at that, so this paper was published in 2018, so these two were the best at the time, okay? We have also looked at black box attacks. So black box attacks are basically what you do is you attack a different classifier. Essentially, you attack, again, this was the best at the time. Now there are better attacks, but a classifier trained on the same data. And so the reason why they were interesting is because what happened was many of the initial attacks were gradient-based attacks. And what a lot of people were doing is they were somehow masking the gradient. So the gradient-based attacks would fail. But if you did a black box attack, which did not know what the classifier was, it would succeed, right? It would train a classifier on it and it would succeed, right? So, so then, for a while, nobody would believe you if you didn't have a black box attack section in your paper. So we have this section, so, people believe us, and hopefully. So, so we did that, and what we found was that the black box attack did not work super well for, so we looked at, so here I'm showing two, but we looked at a few other substitutes as well. So the top was the kernel substitute, the bottom is the neural network substitute. And what we found was that the black box attacks really did not work that well for nearest neighbors. Again, this is, this does corroborate other people had done, around the same time, other people had done studies on transferability, on how adversarial examples transfer between different classifiers. And this corroborates their results. That, so non-parametric classifiers, they're somewhat different. Things don't really transfer so well between them. So this corroborates their results. Okay, so in conclusion, we looked at some, robustness properties of nearest neighbors and, two adversarial examples. We gave a new robust nearest neighbor algorithm, and, and hopefully we convinced you that, at least in this case, it's a mixture of, too few samples, too little data versus different, bad algorithm. And we gave you some experimental results. And basically, these are the references. So the first two are for the sample selection bias stuff I talked about, and the second, the third one is for again. So the third one is for the adversarial example work. And finally, these are the people who did the work. So Songbai and Ishan are my students who really drove the work, and Tara Javidi and Somesh are my collaborators. And with that, I'll just take your questions. Thank you.